Remember, in the previous screencast, we talked about Dalton's atomic theory. And Dalton's atomic theory was first proposed in 1808. That theory remained very well established for about 90 years. And in 1897, J.J. Thomson began experimenting with cathode ray tubes. So over on the right is a picture of J.J. Thomson, and over on the left is a picture of a gas discharge tube, which is also known as a cathode ray tube. Right? In this cathode ray tube, you have a cathode over here on the left, and you have an anode over here on the right, and connected between those is a voltage source or a battery, and then there would be a wire that would be connecting the cathode and the anode together. When you turn the electricity on, or when you allow electricity to flow through that wire, light rays will travel from the cathode towards the anode. So they travel from this left side towards this right side. It's also important to know that the cathode end is the negative terminal, right? And the anode is the positive terminal. So there are light rays that travel from the negative end towards the positive end. Because those light rays move away from the negative end, J.J. Thomson proposed that the light rays were made up of a negative particle because they moved away from the negative end and they were attracted towards the positive end or towards the anode of the cathode ray tube. J.J. Thomson also did further experimenting with these rays. Over here on the left side, you're looking through the end of one of those cathode ray tubes, and you can see that light ray right there. The reason why it looks arced like that is because around the outside, there is a magnet that's being applied to the cathode ray tube, and the magnet is actually causing that light ray to bend. Regardless of the orientation of the magnet, the light rays were always bent towards the positive pole of the magnet. So they were always bent away from the negative pole of the magnet. That gave further confirmation to J.J. Thomson that that light ray was negatively charged. Over here on the right, he designed a cathode ray tube that had a paddle wheel that ran down the middle. And you can see the paddle wheel right here in the middle of that cathode ray tube. Here, when he hooked up the cathode and the anode on the top to the electricity, the light ray would go through the middle, and it would actually push the paddle wheel from one end to the other. And that suggested to J.J. Thomson that the particles had sufficient mass, meaning that the light ray wasn't just made of light, that there were actually small particles that had enough mass to move that paddle wheel from one end to the other. So from his experiments with the cathode ray tubes, Thomson was able to conclude several different things. First, he called those negative particles electrons. And so therefore, we revised Dalton's atomic theory because now we begin to understand that atoms can actually be divided into smaller parts. J.J. Thomson also established the plum pudding model of an atom. He got the name from the special English dessert down here on the right called plum pudding. Notice in the plum pudding there's a bunch of cake, and suspended throughout the cake there are plums. Right, you see all those little plum pieces? And so he thought that that was analogous to the model of an atom, where there was a large positive cloud, and scattered throughout that positive cloud were the electrons, evenly floating throughout the atom. About 10 years later, Robert Milikan conducted his oil drop experiment in 1909. Robert Milikan's photograph is over on the left, and a diagram of his oil drop experiment is on the right. And how this experiment worked was, he took oil droplets and he squirted them into this canister, and then they fell one by one through this teeny little pinhole in this plate. Now this plate is hooked up to electricity to cause it to be charged. So this was a positively charged plate on the top, and down here there was another plate that was negatively charged. As the oil droplets fall one by one through this hole, they are hit with a little bit of ionizing radiation, like X-rays, that causes them to become charged. And then Milikan would look through this little microscope to see what happened to those oil droplets. And what he noticed was that when the electricity was off, the oil droplets were only acted on by gravity as they began to fall, and so they would fall all the way down, and he could get the pace and the speed at which they were falling only by gravity. But when he turned this electricity on, those oil droplets that were affected with the radiation became suspended somewhere in the middle between the positive plate and the negative plate. So as they were falling, they moved away from the positive plate, but they would never quite reach that negative plate at the bottom, and they would become suspended somewhere in here. Milikan was able to arrive at several conclusions because of his oil drop experiment. First, he was able to confirm that electrons do in fact have a negative charge. Because they were suspended somewhere in the middle between those two positive and negative plates, he was able to actually calculate the charge on the electron. Also, by measuring how quickly those oil droplets fell through his apparatus, he was able to calculate the mass of an electron. He was able to calculate the charge of the electron to be equal to 1.602 times 10 to the negative 19th coulombs, and the mass of the electron as 9.109 times 10 to the negative 31st kilograms. And notice that that mass is about 1/2000th the mass of a hydrogen atom. So you would need 2,000 electrons to equal the mass of a single hydrogen atom. Because Milikan was able to measure the charge on these oil droplets and therefore the charge on these electrons, he knew that there had to be an equal amount of positive charge on every atom because atoms are neutral. He also knew that atoms had mass, and that because the mass of the electrons were so tiny, there had to be other particles inside of the atom that would account for that mass. About 2 years later, Ernest Rutherford conducted his gold foil experiment to see if he could learn any more about these subatomic particles within the atom. In Rutherford's experiment, he took a radioactive source that emitted streams of alpha particles. Now, alpha particles are made up of 2 protons and 2 neutrons, so they have an overall positive charge. And he shot those alpha particles through this lead screen that had a very small slit in it, and shot the alpha particles towards this gold foil. Rutherford had originally hypothesized that all of these alpha particles would go straight through the gold foil. In actuality, what happened was many of the particles went straight through the gold foil. Some were deflected at very small angles, and other alpha particles were deflected at very large angles. You can see kind of an enlarged idea of that gold foil with all the different gold atoms scattered through the foil. Some of the particles went straight through. Those are the ones labeled A. Some of the alpha particles were only deflected a little bit. Those are the ones labeled B. Then there were a few alpha particles that when they hit the foil actually deflected back at very large angles, almost back to the radioactive source. So from these results, he was able to come up with some new conclusions. First, most of the atom is actually empty space. So unlike what J.J. Thomson had proposed, this pink circle, remember that was J.J. Thomson's plum pudding model, where all of the alpha particles would have gone through. Rutherford proposed this model of the atom where most of the alpha particles do go through, but some are scattered at very slight angles and others are deflected at very large angles. Because of these 2 alpha particles that are deflected, he proposed that the positive charge of an atom is actually concentrated in the center, and that all of the electrons were around the outside. So it kind of reversed J.J. Thomson's model. J.J. Thomson thought that the cloud was positive and that electrons were scattered throughout that positive cloud. And Rutherford said, no, the entire cloud is not positive, but the positive part of the atom is actually a very small, tiny little dense part in the center of the atom. About 20 years later, James Chadwick hypothesized that the protons that were in the nucleus of the atom only accounted for some of the atomic mass, and he thought that there were other particles that contributed to the mass of the atom as well. So he took a radioactive source that emitted alpha particles, and he shot those alpha particles at a piece of beryllium metal. This blue bar represents that beryllium metal. When the beryllium was hit with those alpha particles, it actually emitted neutral radiation. These dashed lines represent that radiation, but that radiation was not charged. When that radiation struck this piece of paraffin wax, okay, like a piece of wax paper, then protons were actually emitted from that wax paper. You can see these protons coming out on the right-hand side. And so that showed that the particles in the radiation must actually have mass. These particles here, these neutral particles that were being ejected from the beryllium metal, had to have an equal amount of mass as the protons that were being ejected over here. Think like pool balls, right? If one pool ball comes across the pool table and strikes another ball, it will go off in the same direction at the same speed. And that's what was happening with these neutral radiation particles and these protons. So from these results, Chadwick was able to conclude that the radiation that was coming off of the beryllium metal was actually composed of neutrons. He later discovered that the neutron made an ideal bullet in order to split other atoms. Because there was no charge, they didn't interact with the atoms that they struck. He could take that neutron right here, this small, tiny sea green dot, and collide it into, say, a larger atom of uranium. That would cause that uranium atom to become unstable and break apart. And this resulted in something called nuclear fission. And then Chadwick's work later on was used in order to generate the science behind the making of the first atomic bombs. So if we take all of the experiments from the previous 4 scientists, J.J. Thomson's cathode ray tubes, Robert Milikan's oil drop experiment, Ernest Rutherford's gold foil experiment, and James Chadwick's beryllium experiment, we're able to combine them together into a revised atomic theory. Remember that an atom is the smallest particle of an element that still has properties of that element. So you could take a piece of gold foil and break it down into the smallest particles that would still retain the properties of gold, being able to conduct electricity, being malleable, ductile, its density, and those tiny particles would be called atoms. But we now understand that an atom is actually made up of smaller subatomic particles, protons, neutrons, and electrons. In the center of the atom is the nucleus, and it is made up of positive protons and neutral neutrons. In chemistry, we are often writing protons, electrons, and neutrons very frequently, so it's handy to have symbols to represent these subatomic particles. The symbol for a proton is a P with a little positive charge, and the symbol for a neutron is an N with a little 0 superscript. The nucleus is the only part of the atom that has significant mass. Remember that the electrons were very, very, very lightweight. You needed 2,000 electrons to equal the weight of one hydrogen atom. And one hydrogen atom is only composed of one proton. So the mass of the electron is essentially negligible in terms of the mass of the atom. So all of the mass of the atom generally comes from this nucleus, where all the protons and neutrons are clustered together in the center of the atom. What makes each atom unique is that each element on the periodic table has a different number of protons in its nucleus. For example, carbon has 6 protons in its nucleus. Oxygen has 8 protons in its nucleus. Hydrogen, as I mentioned before, only has 1 proton in its nucleus. The electrons surround the nucleus in a large cloud. The symbol for an electron is an E with this tiny little negative superscript. Remember that the mass of the electrons are so tiny that they're generally ignored when we're calculating the overall mass of the atom. It's also important to remember that atoms are electrically neutral, which means even though they have these negatively charged electrons, they also have an equal number of positively charged protons, and the number of electrons and the number of protons have to be equal to each other so that their opposite charges will cancel out. If you look at the 2 pictures at the top of this screen, and you count the number of protons compared to the number of electrons, they should be equal. So over here on the left-hand side, we have 1, 2, 3, 4, 5, 6, 7 protons, and we should have 1, 2, 3, 4, 5, 6, 7 electrons. Over here on the right, these red dots, those are my protons, and there are 1, 2, 3, 4 protons. And then surrounding the outside in the electron cloud, there are 1, 2, 3, 4 electrons. So in a neutral atom, the number of protons and electrons are always equal to each other. Because there are protons and neutrons clustered together in this tiny nucleus, it's important to recognize that there are many different nuclear forces going on that keeps that nucleus together. all of those protons that are clustered together in the nucleus are all the same charge. So there are repulsive electromagnetic forces that want to push that nucleus apart and cause those protons to get as far away from each other as possible. But there is a strong nuclear force that actually holds those protons and neutrons together, kind of like a glue that keeps that nucleus compact. The net force on the atom between those repulsive electromagnetic forces and those attractive, strong nuclear forces determines the atomic radius of the atom. And you can measure the atomic radius by locating the center of the nucleus and traveling to the very outside edge of the outermost electron cloud, just like the radius of a circle. Now, because atoms are very, very small, they're often measured in very tiny measurements called angstroms, which is 10 to the negative 10th meters, or in picometers, which is 10 to the negative 12th meters.